Well, I thought I'd make a little video here to help clear up some of the common confusion related to Newton's third law. First of all, it's often called Newton's third law of motion. And actually, the third law says nothing at all about motion. So let's just get that idea out of your head to begin with. That we don't need anything about motion. The first two laws certainly do, but not the third. And it's common to confuse what we call Newton's third law of force pairs with another similar kind of concept called a net force pair. So I'm going to show you some common examples, things you've seen before, and help you understand the distinction between the second law and third law force pairs. So let's start with a very typical example, something we've already dealt with before. You probably have in your physics class if you're not in mine, and that's how we draw the forces acting on an object that's sliding across the floor. And we've got a person pushing a box, so we could say Bobby pushes a crate rightward across the floor. And maybe we're just asked some questions about this, and we're going to try to draw the force diagram or the free body diagram showing what all the forces would be on the crate. And it's pretty important in a problem that you know what is the object of interest. We usually call it the system that you're trying to study. What is the object about which you want to know the motion, or maybe you're asked about some forces. I usually underline it in a problem, and that's the object on which you want to draw the forces. And I'll show you why. And when you get into Newton's third law, you have to know what object you want to draw forces on. So we usually draw the floor like this and put the crate something like that. Don't have to draw anything real fancy. And then we start drawing and labeling things. So perhaps we've got Bobby pushing rightward, and we usually try to draw tails on the object. So we will call this the force of Bobby. It's commonly just generically called an applied force, but if I know the name of the thing doing the pushing, I always put that in. We call that the agent, or sometimes the source of the particular force in question. Anytime you have surfaces, you always have a normal force that's perpendicular to that surface. And that's the floor pushing straight up. So we'll call that normal. And we always have gravity. I don't think I've seen a problem yet where we wouldn't have some gravity. So there's different abbreviations for this. I'm trying to be real clear by putting slightly longer abbreviations. And in a typical floor, we're going to have some friction. And so we'll call this the force of kinetic friction, since we're actually sliding across there. So those are the typical forces. And let me show you what I mean by a second law force pair. If this object is accelerating across the floor, it's because either Bobby's force is bigger than the force of friction, in which case it's probably going to get faster as it moves rightward, or maybe Bobby's push is smaller than the force of friction, and this object is getting slower as it moves. But in any event, those two forces combined together make a net force in the horizontal direction. These two forces, the vertical forces, make a net force in the vertical direction. Although in this situation, we wouldn't have a net force because there certainly wouldn't be any acceleration up or down, and so the net force would be zero. But nevertheless, we could still combine those together through vector addition, and really would look like subtraction to most people, showing that those things total up to zero. So that's all about Newton's second law. We really haven't even mentioned third law. Now let me show you where the third law comes in. Every force that you ever draw on an object has a third law counterpart force. In most problems, we never care about it, we're never asked about it, but sometimes in a problem like I'll show you next, we might need to know something about that. So what would these third law pairs be? Well, let me tell you three important characteristics of a third law pair. The third law pairs are always equal in strength. That means if one is 100 newtons, then the other is also 100 newtons. They are opposite in direction. That means if one's to the right, the other's to the left. If one is up, the other is down. And you can see now already why this can be a little confusing, because I just named a pair up here, normal and gravity. They are definitely equal in strength. They are definitely opposite in direction, but they are not third law pairs. It's missing a very important characteristic, and this is the third one. Of the same nature on different objects. That's sort of two in one, but I'm lumping it into one. So what do I mean of the same nature? Well, if you name one a friction force, then its third law counterpart is also a friction force. If one is applied force, then its counterpart is an applied force. If one is gravitational, the other is gravitational. You see what I mean? So let's just describe what these third law counterparts would be. And I'm going to write them in red. We would never ever draw them on the crate. The third law counterparts are never ever on the same object. So third law counterparts in red again. The normal force, that's the force of the floor pushing up on the crate. The third law counterpart is the force of the crate downward on the floor. So the name of the thing that was doing the pushing on this object is the thing being pushed in its third law counterpart. So here we have Bobby pushing rightward on the crate. The third law counterpart is the force of the crate on Bobby. And that would be leftward. Now, if you're Bobby, you're probably here behind the crate giving it a rightward push, and you can feel something pushing against you. That's the third law counterpart. That's the crate pushing back on Bobby. Now, the Bobby's alive and is consciously trying to push the crate. Of course, the crate is not alive and doesn't consciously do anything, but you don't have to be conscious to exert a force. So, what about the third law counterpart to gravity? What is gravity really? Here's one of the most commonly misunderstood ones. The Earth's gravitational field exists because of the mass of the Earth. So it's really the entire Earth pulling downward on the crate. The third law counterpart is the force of the crate upward on the Earth. We don't say it's upward on gravity. Gravity is more of the concept, I guess the mechanism we call it. But the object that does the exerting is the Earth. So it's the thing that gets pulled by the crate. Now this surprises people. They don't realize that crates can pull up on the Earth. But gravity goes both ways. Everything with mass pulls on everything else with mass towards itself. Everything's attractive. So yes, that exists. And notice it's equal in strength. That means however many newtons of gravity force that this crate experiences by the Earth is just the same amount that the Earth experiences from the crate. Yes, that is true. Could it be measured? Well, no, not very easily. We just have to trust Newton's third law in this case. Here's our fourth force here. This is the floor pushing leftward on the crate. And the third law counterpart is the force of the crate rightward on the floor. We are almost never asked questions about any forces on the floor, so we would never really draw that on any real problem unless we were specifically asked for a third law counterpart force, which is something I do in my class. So every force we've drawn has a third law counterpart. So I said it might come up in some problems where you would need to know this. Let me just show you an example. What if instead of pulling the crate across a floor, we had some platform on wheels? Maybe it looks something like this. And so the platform was free to move. And maybe we're going to pull with a rope like this. So we have a person going to pull rightward with a rope. So when might we be concerned with third law pairs? Well, do you see that now the platform itself, which is kind of taking the place of the floor, it could also move. So we are maybe going to need to know the forces both on the platform as well as on the crate. And here's how this looks. I know you have some problems, at least in my class in chapter 7 like this, where if we've got a friction force, so perhaps the crate is slides rightward on the platform. So in other words, the platform and the crate start to move relative to each other. So if we draw forces, I think I'll draw these forces in green since I already have some black ink on here. If the crate is moving rightward, then we have friction leftward. And that's a kinetic friction because there's actual sliding going on. So what is that? That's the platform exerting a leftward force on the crate. So I'm going to draw its third law counterpart. The crate is going to exert a rightward force of friction, also a kinetic friction. See, they have the same nature, and it's just as strong as that is strong. What other forces would interact here? Well, if we have surfaces, we also have normal. So we have the platform pushing up on the crate with a normal force. And we have the exact same size normal force of the crate pushing down on the platform. So those are a third law counterpart. They must be equal in size. So as soon as you know one, you will also know the other. This is a way of kind of filling in some numbers in a problem where you think, well, how would I ever know this? You've got to use Newton's third law to kind of fill in those missing pieces. And those would be the only forces that would be an interaction pair between the platform and the crate. Not that there are other interaction pairs. I'm not going to draw all of them on here, but certainly the crate has that same gravity force that we drew in the last example, and it would have a third law counterpart. We would have the rope pulling rightward on the crate, and the crate would pull leftward on the rope. There's a third law interaction pair. So these pairs are everywhere. But if you're asked about the motion of the platform and you need those forces, this is a great way to get it, is just to look at the forces that the platform is exerting on the crate and use Newton's third law. So let's use one last example here. Maybe we take the crate and it's in free fall. Okay, draw little motion tails like that. So what's the only force we have? The only force we have for something in free fall is downward pull of gravity. That's the entire Earth's gravitational field pulling down on the crate. Now, I'm probably not going to draw the third law counterpart anywhere because I'm never going to be asked about the motion of the Earth. But its third law counterpart would be the upward pull of the crate on the entire Earth. And yes, the Earth would, in a very minuscule way, respond to that force with a little bit of acceleration, not nearly as much as the crate will respond with some acceleration, because Newton's second law tells us that the acceleration is inversely proportional to the mass. So the one with the really big mass, in this case the Earth, has very, very little acceleration. So just because there's what seems like motion for one object and doesn't seem like there's motion for the other, people want to think there's no forces there? Absolutely not. You will always have a third law pair on any problem that you have. It's just a question of whether you're going to need that to solve the problem or not. So that's quite a bit there, but it's an important concept. So hopefully this has been worth your 14 minutes of time or so. I think we'll end it here.